Okay, so I think we can start. So welcome everyone to this Arqus JNI webinar on artificial intelligence. My name is Martin Holler. I'm working at the ID Lab of the University of Graz. And today I'm going to try to provide a general audience introduction to the mathematics behind generative AI models in imaging. And I try to keep it as simple as possible. I will try to use not too many formulas and only one mathematical proof. So let's see how this works out. If you have any questions, feel free to interrupt me and ask them anytime. Okay, so before we dive deeper into the talk, let me start with a short introduction and basic introduction to the topic. So what actually is a generative AI model in imaging? And the simple answer would be, well, it's a machine learning model that allows you to create beautiful images, right? So you can prompt it and you get all kinds of images. Well, then the question would be, okay, this is very nice, but why is this actually useful? I mean, this is not an everyday task that I have that I want to create some images. And one reason why it could be useful is because you can also create images conditioned to some user input, right? You can tell it, I want to have an image of a cat, and the model will create an image of a cat. And I can tell it I want an image of a house, and the model will create an image of a house, and so on. If you want to see a car, you get a car. Well, this is maybe even a bit more impressive and slightly useful, but still, if you're not a professional content creator, the question remains, what does this actually help? What is the use for you? Another answer could be, well, the prompt that you can condition the model to, it's not necessarily a text prompt. You can also condition it, for instance, to a low resolution picture. So say you have taken this picture of the rainforest and you have spotted a nice colibri inside the picture. And now you would like to see this colibri in more detail. You would like to get a nice picture of the colibri. Well, you can prompt the Gen AI model with this low resolution image and actually obtain a high resolution image from that. So this is now even more useful, but still, I mean, this is a multi-billion-dollar industry. So the question is there any serious use case behind this, or is it just to make your vacation pictures a bit more pretty? And to that one can answer yes. Actually, there are also quite serious use cases behind that. And one is medical imaging, because in medical imaging, in particular MR imaging, but also CT and PET imaging, for instance, one faces a very similar problem. So image super resolution is a prototypical imaging problem. And for instance, in medical imaging, the task that you have to achieve to reconstruct an image from the person inside the scanner is actually quite similar. So you again want to reconstruct something like a high resolution image from low resolution measurement data, only that the measurement is a bit more complicated. And also here is actually a state-of-the-art research topic, how to use generative AI models to fulfill this task and to create high resolution images from low resolution measurement data, for example, in MR. So this sounds like a quite decent and serious use case. But then you might say, okay, well, if I look at this image here in the center, I don't see many details. And all of a sudden, the AI model came up with all these details, right? And if I look at the colibri, it's again, I mean, it's apparent that this information I see on the right is actually not contained in the data. So it seems that the model is kind of inventing something. And the question that arises here, well, is this actually safe? Can I use these kind of models for medical imaging? And the answer to this question would be, well, it depends. We have to look a bit into the inner workings of these type of models. And this is something I would like to address in this talk. Okay, so with this short outline, so we would like to provide you actually an outline of the sections of my talk. So in the first part, I will try to explain you a bit about the distribution of images, how you can represent images at the computer, and how you can actually describe them in a probabilistic way. Then I will talk about how to learn the distribution of images, how this can be done on the computer. Then I will go from prior to posterior. So how can we go from unconditional image generation to conditional image generation? And at the end, I will again come back to this application to MR imaging and try to show you some real-world examples, actually. Okay, so let's first look at the distribution of images. And as I said, I'm going to try to start very basic. So if you look at an image, so for instance, this MR image here on the right, and you zoom in very closely, you will see the pixels of the image, right? And the pixels are actually the way how the computer stores these images. So if you're considering here grayscale images, so the way the computer processes these images is nothing but a big array of numbers. For every pixel, you have a certain number, which corresponds to the gray value of this image. And storing and processing an image from the computer is nothing but processing a big array of numbers. So usually we just sort it into one big line, for instance, by going in this direction along the pixels. So if you want to deal with images on the computer, you can remember you just want to deal with numbers, basically, that represent the gray values of the pixels. So in that sense, you can say, okay, all possible images of a certain dimension D actually correspond to all possible vectors X in the unit interval to the power of D. So this is a hypercube. Okay, so if D equals 2, so if you have 2 pixel images, we can easily visualize this here. So it's basically we have 1 pixel value and 2 pixel values, and all possible combinations of pixel values can be represented by these points in the plane. Okay, so this is of course, this is very low dimensional. It's just for visualization, but this is a very important analogy we need to understand for this talk. So any image, if I'm considering the simple case of 2 pixels, I can represent with a point in the unit square. And if I would have a 3 pixel image, I can represent any of these images as a point in the unit cube in 3D, right? But of course, we don't have 3 pixel images, but we have, I don't know, 512 square pixel images. So we have a 512 square dimensional unit cube. Okay, but the principle is exactly the same. So we just have a very high dimensional unit cube, and every point in this unit cube actually corresponds to 1 image by going from taking this point, looking at the numbers it represents, and drawing the pixels according to the gray values that these numbers represent. And if you look now at this representation in 2D, we can say, okay, well, maybe this point here in the unit cube, this corresponds to just a noisy image, right? So it's just one random sample of all possible images I can draw in a computer. If you look at another point, I will most likely also get some random noise image. But somewhere in this point cloud, I also have my MR image, right? This is also one of all the possible images that live in this unit cube. And if I look at another point, I will see maybe another MR image or something similar. If I look at another point, maybe I see an image of a parrot, right? So all possible images of a fixed resolution are contained in this unit cube. And now, this, as you can see, this is quite unstructured, right? And I can get any kind of image, but actually, if you're interested only in MR images, then maybe this set has a little more structure, right? So MR image is not just a random combination of pixels. We have some content in the image. There's some relation between neighboring pixels. There's something you can see in the image. So most likely, if I want to represent all possible MR brain images in the space of all possible images, it will not be just any point in the unit cube, but it will be a certain point cloud that has some structure, like a low-dimensional structure, you can imagine. Okay? And this is really the basis for representing these images with generative models. Because now imagine the set of all possible MR brain images that exist in the world. So think of all humans that exist, all possible time points, and all possible images that you can take of the brain of humans using a certain fixed resolution, for instance. And then we can sample. So this is a huge set of images, right? And we can take samples of this set. And every time we take such an image, we will get 1 point in this plane or in this cube. And if you continue sampling, we get more points. And if you continue sampling, we get more points. And so on. So we get more and more points. And we can start to observe again this structure, right? That we don't get random points. I mean, we get some outliers, of course, but we don't get completely random points. But there seems to be quite a strong structure here. And actually, if we continue this process and count the average number of images that we observe at every possible position in this cube, we obtain something which is called the probability density. Okay, so this is a function. It's a function that assigns every value in this unit cube to a real value in R. And this real value corresponds to the probability of observing this image. Okay, so any image is a point. And the probability density of images gives you, for every possible point, the probability that you observe this point. And you can approximate this by sampling all possible images, averaging, and basically drawing this in a continuous way. Okay, so we can think of behind all possible MR images that exist in the world, there's actually a probability density. Okay, and the interpretation of this probability density is, if the value is large, it means that this image is more likely. If the value is small, this image is rather unlikely, right? So this density will have probably small values in this area looking at the probability density of all possible MR images, and they are not located in this area, but we'll have higher values along this low-dimensional subspace. And now, if you want to generate a random image, a random MR image, actually you need to just generate any point, but not a random point, but a point that somehow follows this probabilistic structure. So you would like to generate points that are mostly in this area. Right? If I want to sample random MR images, I want to look at this probability density, and I don't want to sample anywhere, but I only want to obtain points along this area. And let's see now how this can be done. So imagine we know this density. So imagine we have sampled all possible MR images that exist, and we have this density explicitly. Okay, so we have a function that takes any possible image and assigns to it a value depending on how likely this image is. Then we can use a very basic algorithm actually to draw random samples, and this is called rejection sampling. So I take any random image, and I take a random number between 0 and 1, and then I just look at the probability of this random image that I have drawn. Most likely this will be very small, and this number will just be something between 0 and 1. So this is uniformly sampled. So in most cases, you will actually be larger than this probability, and I will not accept the image. So I will have to make another sample. But if I continue this process, at some point I will be lucky and obtain an image where this value is high, and this random number u is less than the probability of the image, and then this is the image that I generate. So this is the most basic algorithm to generate random samples from a density. Okay, so if I have this density, I can follow this procedure. It might take a lot of time. So basically, I'm just generating random images all the time. And once I have found one that has a certain probability above a threshold, I'd say, okay, this is maybe an image of my distribution. This is maybe an NMR image. And if I do this once, this entire loop, then most likely I will get a point on the plane that corresponds to something like an MR image. And then I can repeat this process, get another point, and I can continue, and I will get more and more samples of MR images. Okay, so with this, we have, at least in theory, a procedure to generate MR images, like a generative model, right? So we have two main steps. So first, we need to kind of learn, we need to represent the probability density by looking at all possible images and storing their probability. This is step one. And step two, I use this simple algorithm to generate random samples from this distribution. So in principle, we have one of the most basic generative models now. However, there is a caveat with that, and this is the so-called curse of dimensionality, because as I told you, like images, they are not 2-pixel images, right? They are 512 square pixel images or more. So we are actually sampling not a point in a unit square or a unit cube, but in a very, very high dimensional cube. And just to give you a feeling about how high dimensional this is and how impractical this becomes, let's look at images which have 128 times 128 pixels. So the dimension D would be 16,384. And I'll say I store every pixel value with an 8-bit number. So this is standard. Then if I want to store this probability density, so this is what I have seen this function, right? I would need 256 to the power 16,384 byte, which corresponds roughly to 10 to the power 39,479 zettabytes. Okay, and just to give you a feeling how large this is, so the estimated global internet traffic in 2025 was 8.8 zettabytes. So this is completely feasible, but way far away from anything that is feasible, right? So we cannot, so while this works in principle, we can in principle obtain this density in this form. It does not work in practice. And also the sampling method is actually unfeasible. So assume that my set of plausible images has 10 to the power 1000 elements, which is already quite a lot. So this is very conservative. Then if I look at this sampling algorithm, I told you we just draw random samples. And once we have found the likely image, we accept it, right? So we can look at the acceptance rate. So how long do I need to sample on average to generate one image? And the acceptance rate for this process would be 10 to the power minus 38,500, which means if I continue this process to sample an image, it would take roughly around 10 to the power 38,400 billion years to sample one image. And again, the age of the universe is 13.8 billion years. So again, completely infeasible. So it works very well in 2D. We can also visualize it in 2D, but the curse of dimensionality kills you whenever you have any reasonable image size. Okay, so we need another method. And this is now what I would like to discuss in the second section of this talk. So how can we actually make this feasible? We want to do basically the same, but we want to do it in a way that is feasible and can be implemented on the computer. Okay, and the first approach is how to represent this density, right? So we cannot just store it. And this is where neural networks come into play. So neural networks are just is a generic class of functions that allow you to parameterize functions. Okay, so but they are particularly well suited to parameterize high-dimensional functions. So a neural network depends on some weights. In this case, they are called theta here. So these weights you can tune as you want, and for every choice of weight, you get a function. In this case, you would get you could say get a function from Rd to R, for example. And now, if I want to find a good neural network, I need to tune these weights. I need to find the correct weight such that the function does what I want. In our case, I would like to find the neural network that represents this probability density function as good as possible. And let me just show you. So for different values of this parameter, we get different functions. But if I plug in, say, these values for the weights of the neural network, I maybe get this density. And in analog, again, in high dimensions. If I change this first weight, maybe the density stretches out a bit. If I change the second weight, maybe the kink becomes a bit more sharper. Okay, so I can tune my parameters, and for every choice of parameters, I get a different function. And the goal would now be to select these parameters in a way that I approximate the density. So basically, I want to find a low-dimensional representation of this very, very high-dimensional density. So the question is, how can we do that? So we don't know this density, P of x, right? So this is the true unknown probability density of all possible MR images, but we want to approximate it with a neural network. And the degrees of freedom that we have are those weights theta. So we can try to play around with those weights and try to tune them such that this parameterized density P theta is as close as possible to the true density Px for all vectors, for all images of a certain resolution. So the question is how we do that. And the problem we have here is we actually don't have Px, right? First of all, we cannot obtain it. Even if we could, we cannot store it because it's just too large. We don't have Px. So how can I approximate something that I don't have? Well, what I have is I have example images. So I can put many patients in the scanner, or I can create images, and I can create a set of training images or example images, say x1 to xn. And then we can try to pursue the following ansatz. So assume P theta is a probability density. Then if I plug in the first image of my training set, P theta of x1 is actually the likelihood of this image, right? And if the image is a real image, I want this to be high, right? If I would have the true probability Px, this value would be high. So also for my approximate probability P theta, I want this value to be high. And likewise, if I plug in all the images, and I assume they are independent samples, then the likelihood of all these images that I observe is actually just a product, P theta of x1 times P theta of x2, and so on. Okay, so I can compute the probability of my set of images under my parameterized density. And I know if the density is the true density, then this value is probably very high. So what I just do is I maximize this value. So I want to find the parameters, theta, these are my degrees of freedom, such that this value is as large as possible. And a maximization problem is actually something that you can implement easily, not easily, but you can implement it on a computer. So basically, we have reformulated the task of approximating this unknown probability density as searching for the parameter theta of a function P theta, under which the observed images are the most likely. So we need to solve a maximization problem, and this can be reformulated to a minimization problem by default, but it doesn't matter. And these kind of problems can be solved using derivative-based optimization algorithms, for example. Okay, so this is something you can solve numerically by using derivatives and certain methods, and you can actually try to find parameters such that this value gets maximized. I put here solved under parentheses because they are very complex problems, and you can hardly guarantee that you have solved them globally, but at least you can get a good approximate solution that suffices for your purposes. Okay, so this is part one. We have found now a way how we can learn this density from data. We need the samples of our images, we need some neural network architecture, and then we tune the parameters in an optimal way such that our samples are most likely given this architecture. The second question is, how do we sample from this density? Now, assume we have carried out this process well and we have found an approximate density. How can we use it to generate images? And here there is an alternative algorithm that actually does not directly suffer from the curse of dimensionality, and this works as follows. So again, I initialize with a random image, but now I carry out, say, a certain number of iterations. And I look at the derivative of my density at this current image and slightly move around in my space of images. I move in a direction where the probability of this image becomes higher. And then in order to create randomness, I also add some noise. And I do this a certain number of times, and then I return the image. So we can try to visualize this. Basically, I initialize randomly, but instead of looking now at the probability at this point, I just look at how the probability changes if I move around a bit. And then I move in the direction where the probability becomes larger. And I repeat. I move again, and if I iterate this long enough and under certain conditions, I can actually obtain indeed a sample from my density of images. And this is an algorithm that is actually numerically feasible. So with this, I can create samples even of high-dimensional images. So in the ideal case, for instance, I would then have obtained an MR image. Okay, so this completes like one part of the talk, right? So now we have learned how we can approximate the density of images using neural networks, and we have also learned how we can sample from this density. Okay, so in principle, we have a method to generate images, please.
Is there an estimate on how large the error is of this learn?
Yes, there are convergence rates. So, you know, I mean, you will never exactly approximate the probability, but you can basically look at the distribution of the probability distribution of the samples that you generate with this algorithm. And you know that this converges to the ground truth distribution, depending on how many iterations you use and depending on some conditions. So there are like bounds on this error rate. Okay, so the next question is, how can we now use this parameterized density that we have trained, for instance, in MR images to actually reconstruct MR images, right? We again need some conditioning. We don't want to sample a random MR image, but we actually want to obtain the MR image that fits to some measurement data. So how can we involve measurement data? So we come to this next section to talk about this. And now to consider this, I need to make a short detour and explain you like the basic concept of conditional probability. Okay, and let's go back one step and assume we are looking at the result of 3 coin flips. So I'm flipping 3 coins simultaneously, and I look at the results. And each coin can have head or tail, and I have 8 possible results, right? All possible combinations of 3 coin flips. Now I could ask you, what is the probability of having at least 2 heads? So can any of the non-mathematicians answer this question? Well, we assume like each of these 8 outcomes is equally likely, right? And then looking now at the probability of a certain outcome. So what I do is actually, I look at how many outcomes are there with 2 heads, and I divide by the total number of possible results. Okay, so this is a basic computation of probability. So I have here all 8 possible results. How many of these results have 2 heads? Well, here I have 2 heads, here I have 2 heads, here and here. So I have 4 possible results with 2 heads, and I have 8 possible results in total. So the probability so since every result is equally likely, the probability of obtaining 2 heads is 4/8, or 1/2. Okay, so now that you know that, and you can compute probabilities, we come to class 2. So assume now we know that the first coin is a tail. What is then the probability of having 2 heads? So now we have some information. We know there was this experiment, and somebody told us, well, the first coin was actually a tail. And now you would like to know what is the probability of having at least 2 heads. And it's kind of clear that it changes, right? Because we know something. So, and actually we know that situation is a bit bad or worse than unknown, because we know there's already one tail. So we would expect this reduces our chance of having at least two heads, right? We have not so many options left. Well, the way to compute this is exactly the same. I just look at all possible results that remain and are the ones that I want to know or want to have, and I divide by the number of all possible results. So I look at how many results are there now with two heads and the first coin being a tail, because I know the first coin is tail. So I restrict myself now to all possible results with two heads, where the first coin is a tail. Right? And if you go through again all possible results, we see actually there's only one. So there's only one result remains where the first coin is a tail and there are two heads. How many results are there in total, knowing that the first coin is a tail? Well, actually 1, 2, 3, 4, right? Here all the first coins are heads. So it's just 1/4. It's the same principle. I look at all possible results that I'm interested in and divide via all possible results. And what we have just done is actually we have computed a conditional probability. So we wanted to know the probability of an event A given that event B has happened. So we wanted to know what is the probability of having two heads conditioned to the fact that the first coin is a tail. So conditioned to some information. And this can be computed by looking at the probability of both, so A and B happening, and dividing by the probability of A. So I was keeping some like division over with the whole probability, but this doesn't matter here. So what we have learned basically is, if I want to look at the probability of A given B, I can compute this by looking at the probability of A and B and dividing by the probability of B. Okay, so this is the definition actually of conditional probability. So now let's go back and no, we go one step further actually. So now we come to like the one only proof of this lecture. So recall again, we have observed that the conditional probability of A given B is actually the probability of A and B divided by the probability of B. And now using this, we can actually prove the famous Bayes theorem. So again, we start with what we know, right? The probability of A given B is probability of A and B divided by probability of B. And now we do one of the most famous tricks in mathematics. We just do nothing. We multiply by 1. So we multiply this expression by P over A divided by P over A, which is 1. Right? The fraction 1, the same number divided by itself is 1. So I'm just changing nothing here. But now I'm reordering the terms. Okay, so we know hopefully how we can compute these fractions, right? So we can just exchange these two terms here in the denominator. So we don't change anything, right? We have just reordered terms. And now actually I look at this first term and I observe, well, the probability of A and B is obviously the same as the probability of B and A. It doesn't matter in which order I formulate this, right? But now if I look closely again at this first red term, I see that this is actually now the probability of B given A. So we have exchanged the roles of A and B. We started with the probability of A given B. And now we have arrived at the probability of B given A, and we have two more factors here in order to make this change, to explain this change. And this is the so-called Bayes theorem, because it allows you to connect the probability of, it allows you basically to exchange the events in conditional probabilities. So let's recall this for now, and let's see now how we can actually use this in our problem. So let's go back to imaging. Again, recall assume we have learned the probability density of all possible images of resolution 1024 times 1024. And now somebody gives us a sample image of resolution 128 times 128. And our task is to reconstruct this full resolution image X. Okay, so we have this image Y on the left, which has low resolution, and we want to obtain this full resolution image X here. And you can see that this is obviously a difficult problem because we need to invent somehow information, right? Some information got lost because the image is in low resolution. How can we get it back? Another crucial observation is that, well, while this direction is difficult, the other direction is actually easy. If I would have the high resolution image, I can easily go down to the low resolution image, right? I can just do downsampling. So I just do pixel averaging or whatever, and I just downsample my image. So I'm interested in going from Y to X, which is difficult, but I can very well describe the process from X to Y via downsampling. And I can do this in the notion of probability. So if I now give you X, the true image, and I ask you, what is the probability of seeing this low resolution image, given that I know the higher resolution version looks like this? You can just compute it, right? You can say, okay, if Y is really a downsampled version of X, then the probability of Y is high. If not, then it's low. Actually, you would even say in this case, the probability is 1 if it's the downsampled version and 0 else, but usually one adds some noise and some errors to make it a bit softer. But it's very easy now to describe the probability of Y given X, right? If you know the high resolution image and I give you a candidate low resolution image Y, you can easily compute whether this is a plausible candidate or not. You just look at the downsampled version of X and compare it to this image. And if it looks similar, then you say, well, this is the right image with high probability. Okay, so in summary, we want to go from low to high resolution in a probabilistic sense. But what we actually can do is we can go from high to low resolution. So we can easily describe the probability of the low resolution image given the probability of the high resolution image. And now we want to turn this around. So actually, in order to create the super resolution image, what we want to know is the probability of X given Y. We have the low resolution, and we want to know what is the probability of the corresponding high resolution image. Okay, and now we can use Bayes' theorem that we have derived before in order to exchange these two in the notion of conditional probability. So using Bayes' theorem, we can say, okay, the probability of my high resolution image given the low resolution image is actually the probability of the low resolution image given the high resolution image times the probability of the high resolution image divided by the probability of the low resolution image. So this was the probability of A given B is the probability of B given A times probability of A divided by B. So the formula we had before. And what we have on the left here, this is basically the answer to our question. Because this says, okay, if this is the low resolution image, I can describe the probability density of all possible high resolution images that fit to this low resolution measurement. And the nice thing is, using Bayes' theorem, we can transform this to the expression on the right. And here we know everything except for P of Y. We know this conditional probability because we know how we can go from high to low resolution, right? So this is just high if Y is a downsampled version of X and it's low otherwise. And this is actually our image prior. So this is the probability of seeing the image by itself. This is what we can learn from data as before. So these two things, we actually know how to obtain them. This first one we can just explicitly write down using modeling. And the second one we can learn from data using this neural network model. So we know everything except for P of Y. But now the nice thing is, if you recall, the sampling algorithm was basically based on taking a random image and moving in a direction where the probability of this image increases. And if I just care whether this probability of X increases or decreases, I don't need to care about Y because Y is fixed. It does not depend on X. So if I want to carry out the sampling algorithm and obtain samples from this density, from this probability, I just need to start with a random image and move around such that this quantity increases. And in order to check if this increases or not, it suffices to have the two probabilities here above, because this does not depend on Y. Okay, and with this, I can actually carry out my sampling algorithm. I have all my ingredients that I need. So let's try to summarize again. Okay, what have we now achieved? So first, we have started with a set of training images, and we can use this to learn our parameterized density p theta. Then we can use Bayes' theorem to actually obtain not only phi theta, so the prior probability of images, but we can obtain the posterior probability, which is the probability of seeing the image given a low resolution measurement. Okay, so conditioned to this low resolution image. And then we can use sampling methods in order to obtain a high resolution image from this low resolution image Y. So these are the three main ingredients. And using methods like this, so for instance, we can actually obtain these results, right? So this is an example from a research paper where on the left is the low resolution image that was the input to the model, and on the right we see a high resolution version. Okay, any questions at this point? Okay, let's go to the last part now. So how can we use this for MR imaging? So let me start with some background. So why actually is this challenging, right? I guess all of you know MR imaging, and actually, I mean, this is something that exists for many years, and it worked already without using generative AI models. So why is this actually a problem? Well, what does MR imaging do? It measures by default the proton density of hydrogen atoms in your tissue. So you're put into the scanner, and the MR machine tries to measure the density of hydrogen atoms because you're mostly based on water, so you have many hydrogen atoms in your tissue. And the data in MR imaging is actually acquired line by line in frequency space. So this is like, basically you can think of, you're in the scanner, there's the image of the brain, and it's more or less acquired line by line. And the problem here is that this takes some time, right? So in order to acquire all the data that you need to measure for a certain amount of time. And the longer you measure, the higher is the resolution of the image that you can reconstruct. If you measure only a very short time, you have only data for a rather low resolution. Okay, so by itself, this is a problem because you want to obtain high resolution images by using only a short amount of measurement time because MR machines are expensive, right? Patient throughput is an important issue. It becomes even more a problem if the patients start moving, right? So if the patient has to be in the scanner for a long time, probably they will not stay still, but they will move, and then you have inconsistent data. So this is another reason. And the third reason is sometimes you might want to image something that actually is moving, like the heart, which you cannot stop. And here time is even more critical, right? So when you want to image something that moves and you cannot stop it, you need to be very fast in order to have consistent data. So for all these reasons, it's an important problem to obtain high resolution images in MR imaging from low resolution measurements. And this is more or less a super resolution problem that you face here. So the measurement space is a bit different. You measure in frequency space, but essentially you get some undersampled data. And from this data, you want to reconstruct an image. And the question is, how can you use AI in this context? And actually, the principle is very similar. So we just need to follow our previous steps. So first, and now I'm considering MR knee imaging because there's a big database of knee images around that we have used in this case. So how can we achieve a generative AI model for MR knee imaging? Well, step one, you train a probability density function on a database of knee images. You look at a big database of hundreds, thousands of knee images, and you train this density, exactly how I described, right? You parameterize it with a neural network. You learn the parameters by maximizing this probability. Then you define this conditional probability, because also in MR, if you know the image, you can easily explain the measurement because you know how MR imaging works. The difficulty is going from the measurement to the image. Please.
How large is this big data?
The network, you mean? That's a choice of the researcher, I would say. So you can, and it depends on what you want. So you can make it very small on patch basis, that you train a model that actually works on small patches of images. You can also make it a model that works on the full resolution image. So this is really varying a lot. So you can go from thousands of parameters to millions of parameters. And there are many different ways to parameterize this piece theta here. So like you can use diffusion models or transformers even, which are even more high dimensional.
To deal with anomalies, train it on a whole bunch of healthy knee images, and now you're looking for an unhealthy knee image.
Yeah.
How does the machine know that an unhealthy outcome is an option?
That's exactly. So this is a question maybe we should discuss at the end. So this is where I'm going at the end. But it's an important question. You're absolutely right. Okay, so let's to go back and complete this, so how can we use this for MR imaging? So as I just said, we can basically, knowing how an MR machine works, we can define this conditional probability in the reverse order, right? So we can define the probability of the measurement given the image, where we're interested exactly in the other way around. And then again, we use Bayes' theorem. So we look at the probability we actually want, so the probability of the image given the measurement, and we turn it around and turn it into the product of the probability of the measurement times the image, which we can model, and the probability of the image that we can parameterize and learn. And as I said, this factor that doesn't depend on X doesn't matter for us. And then we can use sampling algorithms to actually reconstruct the image. Okay, and this would be some results. So on the left, you see a badly resolved MR knee image, and on the right, you would see a reconstruction that was obtained using this kind of approach. And again, now we come maybe to your question, can we actually trust this image, right? What if the person has a very rare knee? What if something is in the scanner that we have not seen before? And actually, this is a big issue, right? So if I go back to this result from this research paper, well, this is the method I think they proposed, but they also compared to some other AI super resolution methods, and one produced this result, right? And the question, well, looking at this data, I would say it's not so clear whether this result is more likely. And of course, this is not something you want to have in medical imaging. And what you can do in this context is actually you can really, so knowing this probabilistic setting that you have in the background, you can do what is called uncertainty quantification. So you cannot generate one sample, but you can, for instance, generate multiple samples of your distribution, and you can try to compute the variance. So you can see how much do the samples actually vary, and do they vary a lot or not? And this you can use as an indicator how trustworthy the reconstruction is. And you can do this either just like as I said, then you still depend on certain assumptions, or you can also include all of this in a statistical procedure, which then really allows you to obtain quantitative error bounds. So if you do the statistics right, you can do this like imaging using these AI models, but you can combine it with obtaining high probability error bounds. So you can say, okay, if I look at this pixel, I have a certain error interval, and I know with 95% probability, my true pixel value is in this error interval that I predict. And I think this is important. So it's important not to make only a point prediction, but to also provide some additional information that tells you about how trustworthy the reconstructed image is that you have. It still not fully answers your question. I will come back to that at the end. But now let's come to the conclusion. So what we have seen today is hopefully how AI models can be used to learn the probability density of a set of images. We have discussed how they can be combined with problem-specific modeling. So we have two ingredients: learning the density of images, and using mathematical modeling or domain knowledge to explain the measurement. And combining these two, we can get a method that is actually useful and can be used in medical imaging like MRCT and PET imaging. So these are all very similar principles. And we have also seen that risks definitely exist, so one has to be very careful with that. But if you understand what is happening, you can at least try to handle these risks with uncertainty quantification. Okay, and there are some further references if you are interested. This is basically the main sources for what I've shown in the talk. And with this, I want to conclude. Thank you. Okay, so maybe, but just to come back to your question now. So I think, so what you can, so the underlying assumption of, I would say, any reasonable machine learning method is that you have random samples of your actual data. Okay, so you have independent and identically distributed samples. If you have this, you can make quite strong guarantees on the reliability of your method. So you can say, sorry?
You have to have trained in specific.
Exactly. So you can even provide explicit bounds that tell you, okay, if I had this and this number of images, I can be certain that my method is correct up to this and this error bar. Okay, but the underlying assumption is always that you have real independent samples of your distribution. So you must be very careful how to obtain your data. You must include all the patients with all the anomalies. If you do not include this, then it's really a problem. So that the main and unsolved question is how to deal with outliers, how to deal with distribution shifts. I mean, there are also methods to approach this, but this is not directly contained in these approaches. So they are really based on the assumption that the training data is representative for your application data later on. Ja, gern. So any other questions, comments?
So we constructed like one P for every part of the body. So each probability function more or less is, so every part needs a new probability function for the V. How does it work with like generative AI? When I give the prompts, then probably those prompt is also another input for the neural network, or because for house I need a new function, for car I need a new probability function.
Yeah. Okay, so I should repeat the question. So the question is, basically it looked like we are just training one probability density for brain images, and then if I have knee images, I need to train another one, and if I have houses, I need to train another one. And how is this actually done in practice, right? So I would say it depends always on how expressive the model is you're training. So I think these really large-scale foundational models, they are just trained on all possible images. So they are trained on house, knee, whatever you can imagine. For medical imaging, this is probably not the way to go. What you can also do is you can train models that have a very limited field of view. So you can train models that don't see the entire image, but they only see patches with 8 × 8 pixels. And then basically they have no chance to learn like the full distribution of images. If you sample from these models, you will not obtain a knee image, but they learn certain structures of images. They learn basically that images have edges, that the edges are maybe smooth, that you have homogeneous areas and so on. And if you combine this with the measurement in a situation where you have enough measurement, it's still very useful. So you still can get quite a significant improvement. If you combine this with measurements that are not enough, then you will not get a knee image. You will get just something not random, but something like has some structure, but not a knee image. But for medical imaging, this is not a problem because you don't want to invent information anyway, right?
Okay.
Questions? Please.
Do you have any comparisons with ground truths? Like in university, you have phantoms.
Yeah. So the question is about comparing to ground truth. I mean, so by default, when you do this model, you always do what is called the train, validation, and test split. So you have a big data set of images. You split it usually into 3 parts. One is the training that you use to train this density. One is the validation set that you basically use to fix hyperparameters. So again, how big should the network be? How many iterations do you need for the algorithms? These are all degrees of freedom that I have to choose. And I choose them based on the results on the validation set. And once everything is done, I look at the test set, and there I evaluate the performance of the images. So in this case, in MR images, this is quite simple because the task is basically to get high resolution images from measurements that only allow for a low resolution reconstruction. But I have always the option to acquire a high resolution image. So I basically make an artificial MR experiment where many test persons lay in the machine for a very long time. I acquire the full high resolution image, and then I artificially throw away part of the data and give the model only the low resolution. And then I have this ground truth to compare. In other, like in CT, this is also quite feasible, I would say. In PET imaging, for instance, this is not so feasible. There are people also use phantoms, as you say. You can either have like software phantoms, but there are also hardware phantoms that you can use for that if you want to really account for the physics of the imaging device. Yes.
To come back to your example of a moving part.
Yeah.
Because you never get your image of a living moving part. So do you also have to train the model on dead parts?
No. Yeah, that's a very good question. So the question was now how to deal with this, how to obtain ground truth data if you want to image a moving heart. So what is done here usually is so-called gating. So you put the person in the scanner and you acquire, so basically in MR imaging, you acquire data line by line, okay? And every line is fast, but you need many, many lines to get the full image. And what you do is you put the person in the scanner and you divide, you acquire lines and lines and lines, and you let the person lie in the scanner and the heart beats normally. But then you also have an ECG that tells you at which position of the heartbeat you are. And then you image, say, 10 or 20 heartbeats, and retrospectively, you collect the data to make up one full heartbeat. So you acquire data from 10 heartbeats. Of course, the person has to be perfectly still and breathe normally and have regular heartbeats. But then you have, for every position of the heart, you have lines at different time points, and then you just say, okay, this is like one image of one heartbeat. And this is called gating. This is what can be used, for instance. Or phantoms again, of course.
Mit vielen Applaus nicht gesehen.
Okay. Schön.
Eine Frage ist so Bullshit.
Okay, ja. Ja, ich schaue gerade. Okay, das dauert natürlich eine Zeit, um das einzugeben. So, jetzt bin ich da rausgegangen.
Was ist?
Okay, follow up about how trustworthy selection. Okay, so I'm trying to summarize this question. So there was basically a follow-up on this, how trustworthy is the information in this super resolution setting? Because of course information is lost. I mean, so my short response would be, so the examples that I've shown, they were very extreme, and the results are of course not trustworthy. So there's just a limit to that, right? I mean, you can maybe do 2 or 4 times super resolution depending on the data that you have. Everything beyond that is really just invention of the model. Depending on your application, this could still be okay. I mean, if you just want a beautiful picture of a coal debris, maybe you don't care if this was the real coal debris that you saw. But of course, for medical imaging, this is not sufficient. So there is a strict limitation of how much you can do, but still you can do a lot. So I think in still imaging, you can now get credible results with acceleration factor of 8, for instance, usually for dynamic imaging even more, because you can exploit redundancies in time. So there's a clear benefit. But of course, the results that I've shown were too extreme, and there is no free lunch. So the model, it can only reconstruct information that is still there, and if the resolution is too low, the information is gone. I hope this answers partially the question. Okay, thank you.